This is John Whitaker for the Probability Graduate Level class, and this is our 21st video lecture. And today's lecture is going to be dedicated to conditional variance. And we're going to start off with the definition of conditional variance. So the definition of conditional variance is as follows. It says, the conditional variance of x given y is denoted by the variance, conditional variance of x given y equal y, and defined by the conditional variance of x given y equal to y is equal to, it is the expected value of x minus the conditional expected value of x given y equal to y, that quantity squared given y equal to y. So that's its definition. And we're going to have a fact. This is, the next thing I'm going to write down is a fact that is analogous to the fact about variance of x. Let me write it down. I have room here. So as a fact, we could say the conditional variance of x given y equal to y, that's equal to the conditional expectation of x squared given y equal to y minus the conditional expectation of x given y equal to y to be squared. So that conditional variance fact is very similar to the fact for the formula for computing variance of just x. Okay, we're going to prove this in the case where x and y are discrete, and the case where x and y are continuous is analogous. So prove, note the variance of x given y equal to y, well by definition that's the expected value of x minus the expected value of x given y to be squared given y equal to y. Okay, and so for case 1, we're going to assume x and y are discrete random variables. Okay, now we'll start off with this. Okay, then the expected value of x minus the expected value of x given y to be squared given y equal to y. Okay. This would be a sum. So it's the sum over all x values of this random variable, x minus the expected value of x given y, this part to be squared, times f, so this is a function of x, we could think of it. So we're taking the conditional expectation of a function of x given y. So it would have here the the conditional probability mass function of x given y, x given y. That's what that would be. Okay, and so this sum can be rewritten, and I'll rewrite it over here. That's equal to, if I multiply that out, it'd be the sum. So here it will be over all x's, x squared minus 2x, expected value of x given y, plus the expected value of x given y to b squared, times, and here we'll rewrite this as just f of x, f of x given y of x given y. We split this up. Remember, this multiplication is in this form. Into three sums. So this is, the first sum is of x squared of x given y, x given y, minus the second sum. So I pull out the 2. Well, let's just write it all down. So it's the sum over all x's of 2x, conditional expectation of x given y, times the conditional PMF here of x given y. And then finally, plus this sum over all x's of x given y, conditional expectation of x given y, b squared, times f of x given y, x given y. Excuse me. Now this quantity right here fits exactly the conditional expectation of x squared given y equals y. So that's part of what we said the answer would be. Here, this is a function of y, so it doesn't depend on x. So remember, that's a random variable with respect to y. So this is 2, should be minus, 2 times the expected value of x given y times the sum over all x values of x times f of x given y plus this is a function with respect to y. We're squaring it. We pull it out. And sum over all x values of f of x given y, x given y. This part we leave alone. We're just going to copy it down. Here, this is minus 2 times the expected value, conditional expected value of x given y. Here, this is nothing more than the conditional expectation of x given y, plus expected value of x given y to b squared. And here, this sum over all x values, we write this down is times. So this is the sum over all x values. What is this? This will be f of x comma y over f sub y of y. So we'll work with that just a little bit more. Okay, that's equal to the conditional expected value of x squared given y minus, well, this will be 2 times the expected value of x given y to b squared. And then plus the expected value of x given y, all that to be squared, times, well, I pull out 1 over the PDF of y, because that doesn't depend on x. Sum of the x values of the joint PDF, f of x given y. And this is equal to the expected value of x squared given y minus 2 times the expected value of x given y to b squared. Here, this is the expected value of x given y. I'm sorry, I forgot. Plus the expected value of x given y could be squared. This is 1 over the PDF of y, PMF of y. And here, if you sum over all x values of the joint, you get the mf of y. So that cancels. So just being clear here, it's expected value of x squared given y minus 2 times the conditional expectation of x given y to b squared. Here's just plus the conditional expectation of x given y to b squared. These are like terms. You have minus 2 plus 1, so you get a minus 1 of them. So I get expected value of x squared given y minus expected value of x given y to b squared. And that's what I get for case 1 when x and y are both discrete. So here for case 2, when x and y are both continuous, I'm not going to do this. I'm just going to write up my usual statement about it being analogous. Then the proof is analogous to case 1. Except we use integrals instead of replacement of summations. And I'm going to call that the proof. Okay, let's look at some examples. So here we're going to let x and y be discrete random variables with joint EMF given by okay, so it's given by this table, by the following table. And I'll write the table here. Okay, so here's where the x values are. Here's the y values. And, the x values can be 0 or 1, and the y values can be 1, 2, or 3. And the chance of x being 0 and y being 1 is 1/8. X being 0, y being 2, 2/8. X being 0, y being 3 is 1/8. Here's 2/8, 1/8, 1/8. Okay? And so here's the direction. We want to find the conditional variance of y given x equal to 0. So I'm going to use the formula we just had to do this. So I'm going to say no. The variance of y given x equal to 0, that's equal to the expected value of y squared given x equal to 0 minus, so it would be the expected value of y given x equal to 0, all that to be squared. Okay, that's what that is. So let's work on that first part. Well, the expected value of y squared given x equal to 0. This is a discrete case. So we would sum over all y values, that's from 1 to 3, y runs from 1 to 3, of y squared, and then it would be the conditional PMF of x of y given x of y given x equal to 0. So this will be equal to the sum as y runs from 1 to 3 of f y squared, I should have written, times f of 0y over f sub x of 0. So we need to find that f of x of 0. Now, f sub x of 0, well, that's the sum over, so f sub x of x is equal to the sum over all y values, y run from 1 to 3, of the joint PMF. So here that's going to be 0y. So that's equal to f of 0, 1 plus f of 0, 2 plus f of 0, 3. And let me just put down the numbers here. So I'm getting 1/8 from the chart, plus 2/8 from the chart, plus 1/8 from the chart, and that's 4/8, which is 1/2. Okay, so I'm still looking here. Okay, so the conditional expectation of y squared given x equals 0, which is equal to this sum, as y runs from 1 to 3 of y squared, okay, it would be f of 0y over f of 0 of f sub x of 0, which we found it to be 1/2. So from our chart, I can see it over there to the right. This would be 1 squared times f of 0, 1, and then divided by 1/2 multiplied by 2, plus 2 squared times f of 0, 2 times 2, plus here it would be 3 squared times f of 0, 3 times 2. So this ends up being, well, this is 1 is 2, and f of 0, 1 is 1/8. So it's 2 times 1/8. Plus this is 4, this is 8, times 0 to 2, I'm looking at 2x. Plus 9, 18, times f of 0, 3 is 1/8. So I end up getting 2 plus 16 plus 18 all over 8. That ends up being, I think, 36 over 8. So let's see. 4 goes definitely into both of these, so it's 9/2. That's what I got for the expected value of y squared given x equals 0. Okay, I'm going to leave the chart up here. Remember, I'm trying to find the variance phase. The variance of y given x equals 0. I'm leaving the chart that gives the joint PMF still on the board on the right. There it sits. And to compute the conditional variance of y given x equals 0, we now need, so the other part we need, is know the expected value of y given x equal to 0. I need to find it and square it. Well, what is that? That's the sum as y runs from 1 to 3 of y times the conditional PMF of y given x of y given 0. That's equal to the sum as y runs from 1 to 3 of y of f of 0y over f sub x of 0, which is found out to be a half. So this is the same thing. I'm going to write it down this way. As y runs from 1 to 3 of 2y, because this was 1/2, so let's flip it, multiply it, so you get 2 times y, f of 0y. Now, that's going to be equal to 2 times f of 0, 1, plus this will be 4 times f of 0, 2, plus 6 times f of 0, 3. And substituting numerical values here, I get 2 f of 0, 1 is 1/8, plus 4 times f of 0, 2 is 2/8, plus 6 times f of 0, 3 is 1/8. So I get 6, 8 is 14, I get 16 over 8, that's 2. That's what I got. Yeah, that's what I got, 2. So, the conditional variance of y given x equal to 0, which was equal to the expected value of y squared given x equal to 0, minus the conditional expectation of y given x equal to 0 to b squared. That's going to be equal to, we did that just a few seconds ago, still on the board, it's 9/2 minus, this part is 2 to b squared. So it's 4, 9/2 minus 4, that's 4.5, that just ends up being 1/2. That's our answer. That's an example involving conditional variance where we had a discrete case. Let's look at the continuous case next. It will involve a joint PMF we've worked with before. So as another example, suppose x and y are continuous random variables with joint PDF here it is, f of x comma y equal to, as I said, something familiar to us, 12x if 0 is less than x is less, 0 is less than y is less than 2x is less than 1, and 0 otherwise. I think we looked at that before. Yes, definitely. So the directions are going to be, find the variance of x given y. Well, again, by formula, the conditional variance is equal to the expected value of x squared given y minus the expected value of x given y to b squared. So I need to find these two things. Okay. Let's see that. All right. Now, the initial expectation of x squared given y equal to y, that's equal to the interval from minus infinity to infinity of x squared times the conditional PMF of x given y, PDF. And then we integrate with respect to x. Okay, but a lot of times, well, we had found this before, and this is by previous work. Where this is going to be non-zero. This is going to be equal to the interval from, well, it's y over 2 to 1/2 of x squared, and then this part is 8x over 1 minus y squared dx. This ends up being the interval from y over 2 to 1/2. I can pull out the 8 and the 1 minus y squared, and I have x cubed dx. This ends up being 8 over 1 minus y squared, x to the 4th over 4, evaluated from y over 2 to 1/2. That ends up being 2 x to the 4th over 1 minus y squared, evaluated from y over 2 to 1/2. You stick in 1/2 and you get 1 over 8 times 1 minus y squared. And then minus, when you stick in y over 2, again, you get y squared over, y to the 4th over 8 times 1 minus y squared. Now, that ends up being 1 minus y to the 4th over 8 times 1 minus y squared. The top factors is 1 minus y squared times 1 plus y squared over 8 times 1 minus y squared. And so our final answer, I'm going to write it right here, for the first part of the formula for the conditional variance, is going to be 1 plus y squared. You know what? I need some, you see cancellations will happen. So here's what I get. We end up getting the expected value of x squared given y is equal to, the cancellations, is 1 plus y squared over 8. And here, I've erased where the joint PDF was, but it's going to be restricted from 0 less than y is less than 1. That's what we have. Okay, now, the other part of our formula for the conditional variance would have us look at the expected value of x given y. We're going to square that. But remember what that is. That's an interval from minus infinity to infinity of x times the conditional PDF of x given y, integrated with respect to x. Again, that's going to be the integral from y over 2 to 1/2. This is going to be x, and by previous work, this is 8 over, or I think it's 8x. 8x. Yes, over 1 minus. We probably did this before. 1 minus y squared. I'll go ahead and do it again. For dx. So that ends up being 8 over 1 minus y squared, integral of x squared from y over 2 to 1/2 dx, which is equal to 8 x cubed over 3 times 1 minus y squared, evaluated from y over 2 to 1/2. We stick in 1/2, it's just going to be 1, so it's 1 over 3 times 1 minus y squared. And then when I stick in y over 2 for x, what we're going to get is y cubed over 3 times 1 minus y squared. And so that's 1 minus y cubed over 3 times 1 minus y squared. That can be simplified too. Let's see. I did simplify it. this is 1 minus y times, this will be 1 plus, it's y plus y squared over, this is 3 times 1 minus y times 1 plus y. Okay, so we end up having 1 plus y squared over 3 times the quantity, 1 plus y. Okay. Before I leave that, let me say something. Here, again, we have 0 is less than y is less than 1. All right, so conditional variance, this problem of x given y, which equals to the expected value of x given y, x squared given y, minus the expected value of x given y to b squared. This part we found, it was 1 plus y squared over 8 minus, this would be 1 plus y squared over 3 times 1 plus y, all that to b squared. And that's where I'm going to leave my answer. All right, there's 2 more facts that I want to do. One of them is called the conditional variance formula. And the other one, and it just relates, in some sense, conditional variance to regular variance. And the other one has to do with compound random variable fact. Okay, so, and it would involve the conditional variance formula. So here's the fact that it's the conditional variance formula. Here's what it says. It says, the variance of x is equal to the expected value of the conditional variance of x given 1 plus the conditional variance, or the variance, I should say, of the conditional expectation of x given 1. So we want to prove that. Proof's not so bad. So here's the proof. No, so I'm going to look at each part of the right-hand side of our formula. So the expected value of the conditional variance of x given y, okay, is, by formula, I can rewrite this as the expected value of, here, this is the expected value of x squared given y minus the expected value of x given y to b squared. Expected value of subtraction is the expected value, it's the subtraction of expected values. The expected value of this part, conditional expectation of x squared given y, minus the expected value of the conditional expectation. So here, this thing's b squared, yep, of x given y to b squared. Okay. So this part, I'm going to use a fact that I mentioned in the last video, and that is, if you take the expected value of the conditional expectation of a function of x given y, that's nothing more than the expected value of x squared. This guy I'm not going to touch. what I'm going to write. So I'm going to leave it alone. Now that was this first part that's involved in our formula. Okay, now I need to do the variance of the conditional expectation. That's the second part of our formula. We're adding those quantities together. Okay, so note the variance of the conditional expectation of x given y. Well, by definition, that's going to be the expected value of the conditional expected value to b squared, and then it would be minus, oh gosh, I'm running out of room. All right, minus, it would be the expected value of the conditional expected value of x given y, whatever that is, all that to be squared in this fashion. So that's equal to, well, that first part I won't touch. Just write it down. So we take the expected value of that minus, here, this by previous fact, the expected value of the conditional expectation is nothing more than the expected value of x, and it needs to be squared. So, we take a look at this part and the previous part. So that means if I take a look at the expected value of conditional variance of x given y, plus the variance of the conditional expectation of x given y, we're adding these things together, then that's equal to, this guy we just found was the expected value of x squared minus the expected value of the quantity, the expected value of x given y, that to b squared, plus, that's that plus, here, this is the expected value of the quantity, the expected value of x given y to b squared minus the expected value of x, all that to be squared. These two guys are exactly the same, except one's minus, one's plus. They're going to cancel with each other. And then, what we're left with is something by formula is equal to the variance. Let me write that down. So that's equal to the expected value of x squared minus the expected value of x to b squared, which is equal to the variance of x. And that ends the proof of the conditional variance formula. Okay. As a last fact for this lecture, has to do with compound random variable. So it says let x be a compound random variable. So we talked about that last time. Where, what does that mean? X is equal to a sum as I runs from 1 to n of x sub I, and x sub i's are independent and identically distributed with the expected value of x sub I equal to mu, that's for each I, and, so they're my finite mean, and variance of x sub I is equal to sigma squared those x sub I and the x sub i's are independent from the integer value, natural value, random variable n, okay? Then the variance of x is equal to sigma squared times the expected value of n plus mu squared times the variance of n. That's what I got. That's what we got. So we want to prove that. It'll take a few minutes. So here's the proof. Well, the variance x by the conditional variance formula is equal to the expected value of the conditional variance of x given n, and so it's plus the variance of the conditional expectation of x given n. So we're going to look at each one of these independently. And the first thing I'm going to look at is this conditional variance and then take its expected value. So note the variance, conditional variance of x given n, that's equal to the expected value of, what is x? It's a sum. As I runs from 1 to big N of x sub i's. That's sum. Given n equal to little n. So when it's this guy squared. Okay? Okay, that's what that is. That guy being squared. Okay, and then it is minus the expected value of this sum given n equal to n. That whole thing should be squared. That's by definition. No, by fact involving with conditional variance. Okay. Okay. So this is equal to, so we'll make one small adjustment. So here we know that big N is equal to little n. So it's the expected value of the sum as I run from 1 to little n, because big N is equal to little n, of x sub i's, that part to b squared, given n is equal to little n. And now minus, this will be minus, so the expected value of these, the minus the expected value of the sum of the x sub I running from 1, you might as well say little n, because big N is equal to little n. That whole thing is going to be nothing more than n times mu squared. N times mu, I should say, b squared. So that has to do with the independence, okay? That's what that's going to involve, okay? That's what we get. So that's a fact, okay? And that's going to be equal to, so let's write this out. The conditional expectation of, here we have x1 plus x2 plus x of little n given big N equals little n minus n times mu b squared. That's equal to, now here, this is going to be equal to the expected value. Oops, this is wrong. This should be squared here. And so I forgot to square it. Okay, if we square this out, we're going to get it as a sum. Well, let's write it out. So it's x of 1 plus x of 2 plus x of n times itself. Given that n is equal to n, minus n mu to b squared. That's equal to, here, this expected value. What do we have when we multiply this out? This is going to be the sum as I runs from 1 to little n of x divided b squared. Because x of 1 times x of 1 is x of 1 squared. X of 2 times x of 2 is x of 2 squared. So, plus, here we have a sum. Well, we have a double sum. So i's running from 1 to n, sum. J being run from 1 to n, and j being different than I. Okay? Here, x of I, x of j, and this is all given. N's equal to little n. Minus n times mu to b squared. Okay, this is equal to, okay, well, it turns out that if you take the expected value of the sum of a given and make that the conditional expectation of the first guy plus the conditional expectation of the second guy. The sum as I runs from 1 to little n of xi squared given n equals to n. Plus the conditional expectation of this double sum different than I, and it was xi, xj, and n, and then minus n times mu to b squared. That's equal to, okay, here, because of the independence, so wait a minute, this step right here, what I just did from the previous step, that's based on a fact that I might ask you to prove, that the expected value of x1 plus x2 given y is equal to the expected value of x1 given y plus the expected value of x2 given y. Okay, so that's based on that fact, from how I got from one step to that step. Now, this step right here is equal to this right here is equal to. Okay. So, by independence, that's equal to the expected value of the sum as I run from 1 to n of the xi squares plus here. There's an independence again. This is the expected value of the sum as I run from 1 to n, sum as j runs from 1 to n, j being different than I, of xi, xj, so those things multiply together, minus n times mu b squared. This is the expected value of the sum, which is the sum of the expected value. Here, I can pull the expected value inside, so the sum double sum of the expected value of xi, xj minus n times mu b squared. Okay. All right, so now all of those expected values of x of I squared, since they're identically distributed, that's going to be equal to the expected value, so it's the sum, so I run from one end, of the expected value of x of 1 to b squared. And then it's plus, do the independence again. This is going to be the sum, as I run from 1 to n, the sum, and j runs from 1 to n, j being different than I, of the expected value of x of I times x of j, expected value of x of j, minus n times mu to b squared. So this is mu. And here, this ends up being n times the expected value of x of 1 squared. Here, this is plus. These are mu's, and we want to know how many we have of them. Where did they come from? They came from taking a random variable for that first collection of x of 1 added up to x of n, times a set different random variable for x of 1 and x of n added together. And so you could switch them, so you could have for each one of them, for each random variable, we had n, we're choosing 2 of them to be involved, okay? And then you could switch the order, so there's 2 of them, and these are all the same, so it's mu times mu, so it's mu squared, minus n mu. This is a lot like the argument we had in the strong law of large numbers group. That's what we have. N times the expected value of x sub 1 to b squared. Here, this is n plus n times n minus 1 times mu squared minus n squared mu squared. So this is n times the expected value of x sub 1 to b squared plus n squared minus n mu squared minus n squared mu squared. These two terms cancel. So I'm left with n times the expected value of x of 1 squared minus n times mu squared, and that is equal to n times the variance of x. That's what I got. So we want to take the expected value of that. So that's variance of x of 1. Oops, let's make that change. I said variance of x, but really it was x of 1. Sorry. So right here, I should have said x of 1. Okay, all right. Okay. And so that's equal to n times sigma squared. So what we just found is the variance of x given y or x given n, excuse me, is equal to n times sigma squared. That's what we found. So the expected value of the variance of x given n is going to be equal to n, or the expected value of n times sigma squared, which equals to sigma squared times the expected value of n. That's part of what we wanted. Now we have to look at the other part. Now, the other part is the variance of the conditional expected value. So let's look at the expected value of x given n, which is the sum, it's the expected value of the sum as I runs from 1 to n of x sub I given, this should be big N equals little n. Okay, which is equal to the expected value of the sum as I runs from 1 to little n of the x sub I given n is equal to little n. And due to independence between the x sub i's and the n, this is equal to the expected value of the sum as I runs from 1 to little n of x sub I, which is equal to, bring in the expected values, the sum as I runs from 1 to n of the expected value of x sub I, but each one of those is the same, so it's n times mu. That's what I get. So, what that tells us is the expected value of x given n is a random variable, big N, whatever that is, times mu. And so the variance, that's what I got to find. Of that almost done. So the variance of the expected value of x given n is equal to hold just a second, I'm sorry. Wait just a second. Need to back up for a second. I've lost where I was doing. Okay. So we had the variance of that, right? Expected value, yes. Okay. I was right this way. So let's look at what we were looking at. So the expected value, here's what we came up with. A variance of x given n. This is part of what was in our formula. This is equal to the expected value of n times sigma squared, which equals to expected value, well, right, sigma squared times expected value of n. And the variance of the conditional expected value of x given n. Okay. This part we just found, that's the variance of n times mu, which equals to the expected value of n squared times mu squared minus the expected value of n mu to v squared, which equals to mu squared times the expected value of n squared. Here I can pull out a mu, and then I need to square it. So this is going to be minus mu squared times the expected value of n, all that to v squared, which is equal to mu squared times the expected value of n squared minus the expected value of n to b squared, which equals to mu squared times the variance of n. So, what I was looking at was the variance of this compound random variable, which is going to be equal to this guy plus this guy by formula, by the conditional variance formula. So that's equal to sigma squared times the expected value of n plus mu squared times the variance of n. And that's what we were trying to prove. All right, that's enough for this video lecture. Thank you very much for your time and patience.